All right, welcome everybody. In this video, we are going to be talking about concepts from section 6.13 of AP Calculus BC, evaluating improper integrals. And so we're going to introduce to you what an improper integral is and how we can find them and, all of the stuff related to this concept. All right, so what are we doing? We're looking at how to evaluate improper integrals. So what is an improper integral? What makes an integral an improper integral? Okay, in general, improper integrals involve infinity in some way. One of the limits of integration is infinite, or maybe both of the limits of integration are infinite. Like one goes to negative infinity and the other one to positive infinity. That's a possibility. Or maybe there's an infinite discontinuity somewhere in the interior of the interval of integration. That's what makes an improper integral improper, is the fact that we've got this function that's going off towards infinity, either a limit of integration or within the interior. So the strategy that we're going to use for approaching these is to replace the infinite part with a variable and the associated limit. And you'll see that a little bit more as we go throughout the lesson, how this is exactly we're going to do this. Once we do that, then we're just going to go ahead and integrate and compute the limit, and we will have found the value of the improper integral. Now, having said that, these are two terms that we have not used before in this course. There are two possibilities for what can occur when we find an improper integral. First, if the limit exists and is finite, we'll say that the integral converges to that value. If the limit does not exist or is infinite, we'll say that the integral diverges. Okay, these are two terms that are going to be very, very important and very common for us to use when we get to Unit 10 of this course. So we're kind of introducing them to you here, and they have a very similar meaning when we talk about what we're going to talk about in Unit 10 as they do now. So if the limit exists and is finite, it converges to that value. If the limit does not exist or is infinite, the integral diverges. Okay, so let's look at the first type of improper integral, the improper integral with infinite limits of integration. So suppose we have a function, and this kind of just breaks down all the different possibilities of things that can occur in this situation. If I've got a function that's continuous on the interval from a to infinity, the integral from a to infinity of f of x can be written by replacing the infinity with a b as the limit of integration, and then finding the limit as b goes to infinity of this integral. Same thing if we have a function that's continuous from negative infinity to some point b, and we're taking the integral from negative infinity to b of the function, we can replace the negative infinity as the lower limit of integration with a letter. We like to use a, and then find the limit as a goes to negative infinity of this expression. And then for part 3, if we have a function that's continuous on the interval from negative infinity to infinity, and we try to take the integral from negative infinity to infinity of the function, we actually have two infinite values to replace here. So what we'll do is we'll split the integral into two parts. We'll pick some convenient number c in the interior. A lot of times we use 0 or 1, but really we can use any number that you find convenient to split it, and we'll split it into two integrals, and then each of these integrals individually will be handled. This one will be handled like it was from number 2 here, and this one will be handled like it was from number 1 here. If we have a situation like this, in order for the integral to converge, both parts of this must converge. If either one of them diverges, that means that the original integral diverges. So that's something for us to look out for. All right, so let's go ahead and we'll look at our first example of an improper integral. We're going to find the value of the integral from 4 to infinity of 1 over the square root of x dx, and if the integral diverges, we're going to state that it diverges. This particular function is continuous on the interval from 4 to infinity. There are no discontinuities in that interval for this function. So what that means is I can go ahead and apply these concepts we were just talking about, and I can replace this infinity with a b, make this the integral from 4 to b of 1 over the square root of x dx, and then take the limit as b goes to infinity. All right, so now I want to integrate. Okay, so I'm going to find the antiderivative of 1 over the square root of x dx. I know that that's just 2, I know that that antiderivative is going to be 2 square root of x. So now we're going to take the limit as b goes to infinity of 2 square root of x evaluated from 4 to b. And we're going to evaluate this just like we did any other definite integral in the past. The only thing is instead of having a number up here as the upper limit of integration, we're going to substitute b in, and then we're going to have to take the limit. All right, so now I put b in. And I think about what happens with this limit. What happens as b approaches infinity to 2 times the square root of b? Well, that approaches an infinite value. And so this limit approaches infinity, and this portion of it approaches, well, is 4. And so this total limit here is going to approach infinity, which means that this integral diverges. Okay? So there you go, your first improper integral. Let's continue on. Another example. Find the value of the integral from 1 to infinity of 1 over x squared dx. If the integral diverges, state that it diverges. So I know that this function 1 over x squared is continuous on the interval from 1 to infinity. So I'm going to go ahead and turn this into the limit as b approaches infinity of the integral from 1 to b of 1 over x squared dx. Then I find my antiderivative. The antiderivative here of 1 over x squared is negative 1 over x, which we're going to evaluate from 1 to b. And so this is equal to the limit as b goes to infinity of negative 1 over b minus negative 1 over 1. And if we take this limit as b goes to infinity, this term right here approaches 0. And so the limit of this expression is going to be 1. And so that is the value of the integral from 1 to infinity of 1 over x squared. Now, if you think about the implication of this for a second, we talked about the relationship between the integral and area. This is saying that if we take the curve y equals 1 over x squared, which, looks something like that, and I take the area under that curve from 1 all the way out to infinity, the area underneath that curve is 1. Okay, that's kind of cool. All right. We mentioned in the opening that there are other types of improper integrals other than ones with infinite limits of integration. There are improper integrals that have infinite discontinuities. For instance, if we have a function that's continuous on this interval but not continuous at the endpoint b, then I can find the limit of that by taking the limit as c approaches b from the left, since the function exists and is continuous to the left of c. I can go ahead and do that in order to find the value of this. If it's continuous on this interval but not continuous at the left endpoint, same thing. I can approach that from the right, find the limit as c approaches a from the right of that expression. If f of x is not continuous at c, where c is in the interior of the interval, we're talking about discontinuities at the endpoints in number 1 and 2 here, but here we're talking about a discontinuity in the middle of the interval. If that's the case, that it's not continuous at c, we're going to break this integral up into 2 integrals, the integral from a to c of the function, plus the integral from c to b of the function, and we're going to use both of these earlier scenarios to break this up. Similarly, similar to what we were talking about when we had infinite limits of integration, when we split it up into 2 integrals like this, in order for the integral to be convergent, both of these must converge. If either one diverges, then the total integral is divergent. And then lastly, if it's not continuous at either of the endpoints, we can again split it up. And this is just like before. We can choose a convenient number in the interior so that we can break this up. Again, both integrals need to be convergent here for this integral to be convergent. All right. So that's what can happen with the interior. Let's go ahead and we'll start working through. We're going to work through a bunch of examples here. We'll go ahead and start with example 3. Yet in this video, I don't know how far I'm going to get. Okay, so I look at the function 1 over the cube root of x. I know that it is discontinuous at x equals 0. So this endpoint right here, the 0, is the problem. So I want to change this over to the limit as a approaches 0 from the right of the integral from a to infinity of 1 over the cube root of x dx. Okay, so now I find the antiderivative of 1 over the cube root of x. Thinking about that, that's x to the negative 1/3 power, and so the antiderivative of that is going to be 3/2 x to the 2/3 power. Wait, wow, I just turned my 8 into an infinity there, just flipped it on its side. Oops. And I'm going to find the limit as a approaches 0 from the right of the integral. This one I evaluated from a to 8. So now I substitute in my limits of integration, and this becomes 3/2 times 8 to the 2/3 minus 3/2 times a to the 2/3. And that's a limit I can take. As a approaches 0, 0 to the 2/3 is just going to be 0, and so the value of this becomes 3/2 times 8 to the 2/3, which is 8 to the 2/3 is 4. So 3/2 times 4 gives us a value of 6 for this integral. 6. All right, I think we're going to cut it off there, just in case. And we'll come back in the next video and we'll pick up with example 4 and finish out the examples from this section. Look at 4 more examples of these improper integrals and how we evaluate them. And then we'll be finished with this lesson for section 6.13. All right, have a good rest of your day, everybody. Enjoy yourself, and I'll see you next time. Bye-bye.